Mid-February 1943, somewhere between Kasserine Pass and Sbeitla, Tunisia. The dust had barely settled when German artillery officers approached the abandoned American position. Olive drab paint, white star. The howitzer sat intact, its trails still dug into the North African sand. Oberleutnant Werner Hartmann had seen plenty of captured equipment in his 3 years of war. Soviet guns, British 25-pounders, French relics from 1940. But this 105mm American piece, this M2 howitzer, would be different. Not because it looked particularly impressive, it didn't. Not because German intelligence had flagged it as a revolutionary weapon, they hadn't. But because what happened when his experienced gun crew began test firing, it would shatter assumptions German artillery doctrine had carried since the Great War. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Battle of Kasserine Pass had just ended. American forces, bloodied and retreating, had left behind equipment, ammunition, and hard-won positions. Among the spoils, several M2 105mm howitzers, some damaged, others serviceable. Standard procedure for the Heereswaffenamt, the German Army Weapons Agency, required systematic evaluation. Captured weapons went east to testing facilities. Technical specifications got documented. Reports circulated to ordnance bureaus. But first, field testing. Right here, with experienced crews who knew German doctrine inside and out. The gun sat on a split-trail carriage, both trails spread wide in firing position. This design feature alone caught German attention. Their standard 105mm light field howitzer, the leFH 18, used a box trail design, a single rigid trail that provided excellent stability but severely limited traverse. You couldn't shift fire to a new target without physically repositioning the entire gun. The American design allowed the barrel to traverse across a much wider arc without moving the carriage. Time saved, flexibility gained. Hartmann's crew consisted of veterans, men who'd served from Poland through France, who'd learned their trade on the leFH 18 and knew its every strength and limitation. They examined the American breech mechanism first, an interrupted screw design, not the horizontal sliding wedge block familiar from German guns. Different, but not necessarily better. Not yet. The ammunition told a more interesting story. Semi-fixed rounds. Shell and propellant combined in a single unit, but with the flexibility to adjust powder charges for different ranges. 7 charge options, from charge 1 for close support to charge 7 for maximum distance. The brass cases looked substantial, well manufactured. American industrial capacity made real. German gunners had heard rumors about American production numbers. Thousands of guns, tens of thousands of rounds per month. Numbers that seemed impossible for an economy that 10 years earlier had been crippled by economic depression. But holding this ammunition, examining these guns, the statistics became tangible. This wasn't propaganda. This was industrial reality. The test firing began simply: standard procedure, load, aim, fire, observe the recoil cycle. The howitzer barked, the shell arcing downrange into empty desert. What happened next stopped the gun commander mid-command. The breech opened automatically, not manually, requiring the breech operator to unlock and swing the heavy block clear, not with the careful, time-consuming procedure drilled into every German gunner. Automatically, the spent cartridge case ejected. The breech sat open, ready for the next round. The loader could immediately insert the shell without waiting. No coordination delay, no lost seconds. Hartmann watched his crew adapt to the rhythm. Load. Fire. The breech opens itself. Load again. Fire. The pattern repeated, faster than anything they'd achieved with their leFH 18, not through heroic effort or exceptional skill, but because the weapon itself had been designed to maximize rate of fire through mechanical automation rather than crew proficiency. They sustained 4 rounds per minute, then 5. Then, during a short burst, 6 rounds left the barrel in 60 seconds. The crew wasn't exhausted. The gun wasn't overheating. This wasn't theoretical maximum performance listed in some optimistic manual. This was sustainable, repeatable capability, baked into the weapon's basic design. German doctrine, refined through decades of professional military development, emphasized precision. Every shell carefully aimed, every fire mission methodically planned, registration rounds first, to bracket the target, then adjustment, then fire for effect, quality over quantity, professional excellence over mass production. The leFH 18 embodied this philosophy, a sound, well-engineered weapon, built to exacting standards by skilled German workers using the finest available materials. That howitzer fired 2 rounds per minute under optimal conditions, sometimes 3, with an exceptional crew who'd trained together for months. But 2 rounds per minute represented the reliable standard German artillery battalions planned around. 2 rounds per minute meant you could deliver sustained fire support without exhausting your crews or overworking your equipment. This American gun was doubling that rate, and the crew operating it had learned the weapon 15 minutes earlier. The German gunners had trained for years on the leFH 18. They understood its quirks, its maintenance requirements, the precise rhythm needed to maximize performance. They knew how to compensate for the manual breach operation, how to coordinate movements to minimize wasted time. Professional artillerists, the backbone of German divisional fire support, and this captured American howitzer, designed for mass production and operation by minimally trained citizen soldiers, was outperforming their carefully crafted German weapon in the single most important metric of modern artillery warfare: rate of fire. Hartmann called a halt to watch the mechanical sequence more carefully. The recoil cycle first. When the gun fired, the barrel travelled rearward, absorbing energy through hydraulic buffers. Then, compressed air in the recuperator pushed the barrel smoothly back into battery position, ready to fire again. Total cycle time, approximately 3 seconds. The leFH 18, using its pneumatic recuperator system, took over 4 seconds for the same sequence, 1.3 seconds, multiplied across a 10-minute fire mission that translated to the difference between 40 shells delivered and 25. In combat, that gap meant the difference between suppressing enemy positions and giving them time to disperse, between breaking up an attack before it gained momentum and responding too slowly to matter. The traverse mechanism demonstrated another advantage. The split trail design let the gun traverse 15 degrees left or right without repositioning the carriage. The leFH 18 managed barely 5 degrees before the crew had to break position, shift the trails, re-level the weapon, and re-establish firing alignment. Minutes lost, opportunities missed. In fluid, mobile warfare, those minutes could decide whether your fire support arrived in time or arrived to find the target had moved. The German officers conferred quietly while the crew continued testing. They documented everything with Prussian thoroughness: measurements, timings, performance observations. This information would travel east to testing facilities at Hillersleben or Kummersdorf, where systematic evaluation would confirm or refute these field impressions. But certain conclusions seemed unavoidable even here, in the dust and chaos of post-battle Tunisia. The Americans had built an artillery piece optimized for different priorities than German engineering tradition valued. Not maximum precision, not theoretical perfection, not impressive paper specifications, but practical, sustainable combat effectiveness delivered by ordinary soldiers with basic training. German artillery doctrine in 1943 still bore the stamp of World War I experience: methodical barrage fire, careful ammunition conservation, professional gunner expertise making the difference. The doctrine worked brilliantly in static warfare, where registered firing positions and pre-plotted targets allowed German precision to shine. It had worked adequately in the lightning campaigns of 1939 through 1941, when Wehrmacht forces attacked enemies who couldn't match German tactical sophistication. But by mid-1943, the strategic situation had transformed. Static fronts in Russia, attritional warfare in North Africa, an enemy with industrial capacity to deliver overwhelming material superiority. The careful, methodical German approach that seemed so professional, so scientific, had become predictable and slow. American artillery doctrine, forged at Fort Sill, Oklahoma, and refined through hasty wartime expansion, emphasized something different: mass fires, multiple batteries hitting the same target simultaneously, volume compensating for any individual gun's imprecision, time-on-target missions where dozens of guns fired at precisely calculated moments so that all shells arrived simultaneously, delivering devastating shock before anyone could take cover. That doctrine only worked if your guns could fire rapidly enough to deliver the required volume before the tactical opportunity closed. The M2 howitzer had been designed specifically to enable that doctrine. Every feature, the semi-automatic breech, the efficient recoil system, the split-trail traverse, prioritized speed of fire and ease of operation. The testing continued through the afternoon. The crew fired different charge combinations, evaluating accuracy at various ranges. They measured shell dispersion patterns. They timed how quickly the gun could shift from one target to another. With each test, the same pattern emerged. The American weapon matched German precision in most categories, while dramatically exceeding German performance in rate of fire and operational flexibility. Maximum range testing revealed another uncomfortable truth. The M2, firing its standard high-explosive shell with Charge 7, reached 12,330 yards, 11,270 meters. The leFH 18, without the muzzle brake modification introduced in 1941, managed 10,675 meters. The American gun could reach targets nearly 600 meters farther than Germany's standard divisional howitzer. Even the improved leFH 18M, fitted with the muzzle brake that increased range to 12,325 meters, merely matched American performance. And those improved versions had entered service only recently, still hadn't reached many frontline units in significant numbers. The weapon American industry had been producing since 1941 already exceeded what German engineers achieved only after 2 years of wartime improvements. The ammunition itself spoke to American industrial sophistication. Each round showed consistent manufacturing quality. The brass cases displayed uniform dimensions. The propellant charges looked identical from round to round. This standardization, routine in American automotive and manufacturing industries, remained aspirational in German production even after years of military preparation. German artillery ammunition came from multiple manufacturers, each introducing subtle variations that affected performance. Gunners had to account for these differences, adjusting aim based on which factory produced the shells they were firing. The Americans had solved this problem through industrial standardization that German industry, for all its vaunted engineering excellence, hadn't achieved. As the sun lowered toward the horizon, Hartmann drafted his preliminary report. Technical language, objective observations, but certain conclusions seemed inescapable, even if stating them too bluntly might seem defeatist. The American howitzer demonstrated superior rate of fire through mechanical design rather than crew skill. It offered greater operational flexibility through its split-trail carriage. It matched German range performance, and it appeared designed for mass production and operation by minimally trained personnel, a design philosophy that assumed industrial capacity and manpower availability Germany simply didn't possess. The report would travel through proper channels. Wehrmacht artillery officers would read it alongside similar reports from other captured equipment evaluations. Some would dismiss the findings, insisting German precision and tactical skill mattered more than crude American mass production. Others would recognize the implications more clearly. But the truly sobering realization wouldn't come from this single field test in Tunisia. It would emerge months later, when systematic testing at German proving grounds confirmed these preliminary observations and revealed even more uncomfortable truths about comparative industrial capability and design philosophy. The M2 howitzer represented something more threatening than superior specifications. It represented an entirely different approach to military industrial production, one that prioritized practical effectiveness over theoretical perfection, that assumed ordinary soldiers could operate sophisticated weapons, that leveraged industrial capacity to compensate for individual limitations. Germany had entered World War II with technical advantages in many weapons systems: superior tank guns, better aircraft, more advanced artillery fire control. But those advantages meant nothing if German industry couldn't produce enough weapons to match enemy numbers, or if German designs required maintenance and expertise that frontline conditions couldn't provide. The artillery officers loading the captured M2 onto a transport truck for shipment to Germany understood this instinctively, even if official doctrine didn't yet acknowledge it. They'd seen the endless American supply convoys. They'd witnessed American air superiority growing throughout the North African campaign. They'd watched German units stretch thinner, while American strength built continuously. This single howitzer, unremarkable in appearance, represented industrial capacity that Germany couldn't match. The question wasn't whether German guns were better engineered in many ways. They were. The question was whether German advantages mattered when the enemy could deliver twice as many shells in the same time period, could produce weapons by the thousands, while German factories struggled with resource shortages, could equip and train crews faster than Germany could replace casualties. The answers to those questions would emerge through continued testing, through battlefield experience, through the grinding attrition that defined warfare's industrial age. But the outline of those answers was already visible here in Tunisia, in February of 1943, in the performance of a captured American howitzer that refused to acknowledge German assumptions about what artillery should prioritize. The truck carrying the M2 rolled north toward the port at Sfax. From there, a cargo ship would transport it across the Mediterranean to Germany. The systematic evaluation would continue, but the field test had already revealed the essential truth that formal testing would only confirm. American artillery had been designed around different assumptions about modern warfare, and those assumptions were proving devastatingly effective. Spring 1943. Hillersleben Proving Ground, near Magdeburg, Germany. The M2 howitzer rolled off the transport railcar, now bearing German designation and markings. Technicians had already prepared comprehensive testing protocols. The gun would undergo the most thorough artillery examination German engineering could devise. Hillersleben, located in central Germany, served as one of the Wehrmacht's primary artillery testing facilities. Here, meticulous engineers measured everything from barrel wear to ammunition performance, documenting their findings in exhaustive technical reports that circulated through the Heereswaffenamt and various artillery commands. The American howitzer was about to receive treatment normally reserved for promising German prototypes. German test engineers conducted the initial static inspection with teams of specialists from multiple technical branches. They photographed every component from dozens of angles. They measured clearances with precision instruments. They documented construction techniques that seemed impossibly straightforward compared to German methods that emphasized craftsmanship and tight tolerances. The carriage drew immediate attention from structural engineers. Where German designs used complex fabrications requiring skilled welding and precise fitting, the American split-trail carriage employed simpler construction methods that prioritized strength and ease of manufacture. The trails themselves were basic I-beam structures, robust but uncomplicated. No elaborate machining, no precision tolerances that demanded factory-level expertise to maintain. This simplicity wasn't crude corner cutting. It was deliberate design philosophy. Every element of the M2 reflected choices that favored field maintainability over workshop perfection. Bolted connections instead of welds wherever possible, allowing replacement with basic tools. Standardized parts that could be swapped between guns without custom fitting. Design margins that exceeded immediate requirements, providing durability that didn't depend on perfect maintenance. The hydraulic recoil system particularly impressed the test engineers. German howitzers used pneumatic recuperators, compressed air and liquid systems that worked reliably but required careful maintenance and frequent adjustment. The American system combined hydraulic buffers for recoil absorption with compressed air recuperators in a configuration that proved remarkably tolerant of varied conditions. Engineers measured recoil forces, buffer resistance, and return to battery timing across hundreds of test firings. The system maintained consistent performance regardless of ambient temperature, a characteristic German pneumatic systems struggled to match. In North African heat or Russian winter, the M2's recoil mechanism simply worked without the constant attention German guns demanded. The breech mechanism underwent particularly intensive examination. The interrupted screw design wasn't. Unfamiliar to German engineers, similar principles appeared in naval guns and some fortress artillery. But the specific implementation in the M2, with its semi-automatic operation, represented sophisticated mechanical engineering applied to field artillery in ways German doctrine hadn't prioritized. When the gun fired, gas pressure forced the breech block to rotate and slide rearward automatically, ejecting the spent case. A simple, reliable mechanism that eliminated the manual operation German guns required. Test engineers fired the weapon hundreds of times, measuring breech operation timing, examining wear patterns, looking for signs of stress or inadequate design. The results contradicted assumptions about necessary trade-offs between simplicity and reliability. The semi-automatic breech functioned flawlessly across extreme variations in conditions, dusty environments that would require extra maintenance on German guns, temperature extremes, rapid firing schedules that stressed every component. The American mechanism kept working. The systematic testing program expanded through spring and summer of 1943. Engineers conducted extended firing trials, pushing the weapon to its limits. They documented operational performance across every variable German artillery doctrine considered important: accuracy at various ranges, ammunition compatibility, maintenance requirements, crew training time, sustained fire capability. Rate of fire testing confirmed the field observations from Tunisia, but with scientific rigor that left no room for interpretation. German test crews, experienced artillerists who trained on the leFH 18, achieved 4 rounds per minute sustained after minimal familiarization with the M2. During short burst firing, they reached 6 rounds per minute without mechanical stress or crew exhaustion. The comparison testing proved even more revealing. Engineers assembled experienced crews on both the M2 and the leFH 18, firing under identical conditions with observers timing every element of the loading sequence. The results, documented in formal reports that circulated through Wehrmacht artillery branches, painted an uncomfortable picture. The M2's semi-automatic breech saved 1.5 seconds per round compared to manual operation. The more efficient recoil cycle saved another 0.3 seconds. The split trail traverse capability eliminated repositioning time for target shifts within 15 degrees. Added together, these advantages compounded into the decisive performance gap German field testing had discovered. An experienced German crew on the leFH 18 could sustain 2 rounds per minute, occasionally reaching 3 rounds during short periods with perfect coordination. That same crew, after brief training on the M2, sustained 4 rounds per minute and could burst to 6. The weapon's design eliminated the need for perfect crew coordination, automated the time-consuming manual operations, and simply made rapid fire easier. By summer of 1943, additional captured M2 howitzers had arrived at German testing facilities. These guns came from different American production facilities, some built by Rock Island Arsenal, others from commercial contractors pressed into wartime production. German engineers examined each weapon, looking for variations in quality or specifications that might indicate manufacturing problems. They found remarkable consistency. The guns from different manufacturers showed fully interchangeable parts. Tolerances matched across production sources. This standardization, mundane in American automotive industry, remained largely theoretical in German tank and artillery production, where each manufacturer introduced subtle variations that prevented true parts interchangeability. The ammunition standardization proved equally impressive. Shells and powder charges from different American production lots showed identical performance characteristics. German gunners didn't need to adjust aim based on which factory produced the ammunition. They were firing a problem that plagued German artillery throughout the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Internal German engineering assessments, intended for senior Wehrmacht officers and armaments ministry officials, documented observations about American industrial advantages that went beyond simple production numbers. These reports, classified and distributed only to those with need to know, revealed how thoroughly German artillery experts understood their disadvantage by mid-1943. One assessment, dated July of 1943, noted that American automotive engineering reflected decades of civilian industry experience. Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership. Vehicles were commonplace among ordinary citizens across all economic classes. Mechanics with automotive training existed in every town. The industrial base for mass-producing complex mechanical systems was mature and proven. Germany's automotive industry, by contrast, remained limited. Cars stayed luxury items for the wealthy. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939. German industry excelled at precision manufacturing for limited production runs, but lacked the mass production infrastructure and workforce training that American industry took for granted. This fundamental difference translated directly into military equipment design philosophy. Americans built artillery that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built artillery that required specialist training and constant expert attention from personnel with years of specific military technical education. The comparison with German artillery reliability became impossible to ignore as field reports accumulated through late 1943 and into 1944. Units receiving the newer leFH 18M variants reported some improvement in operational readiness, but chronic problems persisted. The leFH 18/40, introduced in 1942 using components from anti-tank gun carriages to reduce weight, brought its own complications. German artillery units in North Africa, Italy, and on the Eastern Front sent regular reports documenting maintenance requirements, component failures, and operational availability. These reports, aggregated at Wehrmacht headquarters, revealed patterns that contradicted the image of German technical superiority that propaganda maintained for home front morale. Field reports from units using captured American artillery told a different story. German mechanized units, desperate for reliable fire support as their own equipment degraded under combat stress and maintenance shortfalls, eagerly employed any captured M2 howitzers they could obtain intact. Unlike Soviet weapons, which Germans modified extensively before use, the American guns entered German service without changes. They didn't require modification because they worked correctly as designed, with no fundamental flaws needing correction. German artillery crews who'd experienced breakdowns and constant maintenance demands in their own weapons found the M2's reliability remarkable. Multiple field reports noted that American howitzer operators could focus on tactical fire missions, while German gun crews constantly worried about mechanical reliability. The systematic testing at Hillersleben continued into autumn of 1943, expanding to include comparative doctrine analysis. German artillery staff officers studied American fire direction procedures, examining the time-on-target techniques that American batteries had employed, with devastating effect in North Africa. Time-on-target missions represented tactical innovation enabled by reliable, rapid-firing guns. The concept was elegant: coordinate multiple batteries to fire at precisely calculated times, so all shells arrived on target simultaneously. No warning crescendo, no time for enemy troops to take cover, just sudden, overwhelming destruction from dozens of shells landing in the same 30-second window. German doctrine had nothing comparable. German fire missions followed sequential patterns: registration, adjustment, fire for effect, that gave skilled enemies time to recognize they were being targeted and respond. This methodical approach maximized accuracy and ammunition efficiency, but surrendered the element of surprise that time-on-target missions exploited. More importantly, time-on-target techniques only worked with guns capable of sustained rapid fire. If your howitzers could only deliver 2 rounds per minute, you couldn't generate the volume necessary for truly overwhelming bombardment. The Americans had designed their entire artillery system doctrine, training, and equipment around the assumption that rapid fire mattered more than incremental improvements in precision. By late 1943, the strategic implications were becoming clear to anyone examining the data objectively. German artillery, for all its precision and professional crew training, couldn't match American fire support effectiveness, not through tactical superiority, not through better doctrine, not through more skilled gunners. The Americans had built a system optimized for industrial-age warfare, and that system was proving decisively superior. The testing reports circulated through Wehrmacht artillery commands and the Armaments Ministry. Some senior officers dismissed the findings, insisting German precision and tactical excellence mattered more than crude American mass production. Others recognized the implications but lacked authority or resources to implement fundamental changes in artillery development priorities. By 1944, as Allied forces invaded Normandy and Soviet armies ground relentlessly westward, the artillery disparity became operational reality rather than theoretical concern. American artillery battalions in France delivered fire support with speed and volume German units simply couldn't match. German commanders learned to dread the sudden hammer blow of time-on-target missions that arrived without warning and left defensive positions shattered. German counter-battery fire, once feared for its precision and effectiveness, became increasingly ineffective against American batteries that could fire their missions and displace before German return fire arrived. The faster-firing guns delivered their support and moved, exploiting mobility advantages German howitzers couldn't match. The Eastern Front showed similar patterns. Soviet artillery units equipped with American Lend-Lease M2, howitzers over 4,000 delivered through 1944, demonstrated the same rapid-fire capability that had surprised German gunners in Tunisia. Soviet doctrine, which already emphasized mass fires and artillery preparation, found American guns perfectly suited to their operational preferences. Additional testing at Hillersleben examined various M2 variants as more captured examples arrived. The M2A1, the M2A2, different production batches from different manufacturers. Every variant showed the same fundamental characteristics: excellent reliability derived from sound engineering principles and quality manufacturing processes. The consistency across variants impressed German engineers accustomed to significant quality variations between nominally identical German weapons from different production sources. Some captured M2 howitzers were pressed into German service in the war's final year. Artillery units facing equipment shortages gladly accepted working American guns, overwaiting for German replacements that might never arrive. These weapons served in combat operations on both Eastern and Western fronts, providing final proof of American artillery superiority from the German perspective. German crews operating captured M2 howitzers universally praised their reliability in after-action reports and post-war interviews. The guns simply worked when needed, without constant mechanical attention, without failures that left firing positions silent during critical moments. This dependability, more than any specification advantage, determined tactical utility when German logistics couldn't guarantee spare parts or maintenance support. The contrast with German howitzer performance grew starker as the war progressed. Allied strategic bombing had devastated key production facilities. The Rheinmetall plant at Unterlüß suffered severe damage. Quality control degraded as slave labor increasingly replaced skilled German workers conscripted for military service. Problems that careful peacetime manufacturing had minimized improper assembly. Sabotage, substandard materials became common. German artillery units in 1944 and 45 reported operational readiness rates that would have seemed catastrophic earlier in the war. Batteries that should have fielded 12 guns might have 6 or 7 actually capable of firing. The remainder sat awaiting parts, undergoing repairs, or abandoned due to mechanical failures that couldn't be corrected in field conditions. American artillery, safely produced in factories far from any combat zone and staffed by motivated workers, earning good wages, maintained consistent quality throughout the war. German commanders facing this disparity could only watch as American fire support grew stronger while their own artillery capability eroded. The fundamental difference between American and German artillery development lay not in engineering knowledge, but in industrial capability and underlying design philosophy. German engineers understood automotive principles as well as their American counterparts. They possessed extensive theoretical knowledge and scientific expertise. They simply applied those principles differently, prioritizing factors that made impressive specifications but created poor reliability in field conditions. German artillery emphasized performance characteristics that looked good on paper. The leFH 18 was soundly constructed, professionally designed, built to high standards, but it was heavy for its class, requiring substantial towing capacity. Its manual breech demanded skilled operation. Its limited traverse necessitated repositioning that consumed precious time. All acceptable trade-offs when you assumed highly trained crews and adequate maintenance support. American engineers, trained in automotive mass production through decades of civilian industry experience, designed artillery that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. The M2 powertrain, to use automotive terminology inappropriately but descriptively used components proven in commercial service, with design principles borrowed directly from automobile and truck manufacturing. By spring of 1945, as Germany's collapse accelerated, the captured M2 howitzers at testing facilities prepared for evacuation or destruction. Soviet forces advancing toward Berlin threatened Hillersleben and other proving grounds. Engineers packed critical documentation for transport west, hoping to preserve technical intelligence for post-war analysis, assuming Germany had a post-war future. Some of the captured howitzers, including at least one M2 that had been tested extensively at Hillersleben, were pressed into improvised service with German units desperately defending against the final Allied advances. These weapons fought alongside German designs in the last desperate battles, providing one final comparison under actual combat conditions. The American guns continued operating until destroyed by enemy fire or abandoned when ammunition supplies ran out. German howitzers, including the leFH 18 variants that had been standard equipment throughout the war, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability. Post-war analysis by American, British and Soviet intelligence organizations confirmed what German testing at Hillersleben had revealed 2 years earlier. Systematic examination of abandoned German artillery found mechanical failures, as common as combat damage, as causes of loss. Broken recoil systems, seized breeches, cracked carriages from metal fatigue. The German obsession with precision manufacturing and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built artillery that demanded constant expert attention from skilled technicians, powered by doctrines that assumed methodical warfare rather than industrial-scale mass combat, supported by logistics that collapsed under accumulated strain. American artillery, designed around different assumptions about modern warfare's requirements, had proven devastatingly effective precisely because it prioritized practical function over theoretical perfection. The lessons learned through testing, captured M2 howitzers directly influenced post-war West German artillery development. When the Bundeswehr formed in the 1950s, former Wehrmacht officers involved in planning remembered the artillery gap all too well. They didn't attempt to resurrect leFH 18 designs or rehabilitate German World War II artillery doctrine. Instead, West Germany adopted American weapons and American training methods wholesale. Initial Bundeswehr artillery battalions, equipped with ironically the M2 howitzer, purchased directly from American surplus stocks. German crews trained at American artillery schools learned American fire direction procedures, practiced American mass-fire techniques. The weapon that had humiliated Wehrmacht artillery officers in 1943 became the foundation of German Cold War artillery. By the 1960s, when Germany developed indigenous weapons, the design requirements explicitly included sustained fire rates, matching NATO standards derived directly from M2 performance. German engineers had learned that reliability mattered more than precision specifications, that ease of maintenance determined operational effectiveness, that industrial warfare demanded weapons ordinary soldiers could operate without years of specialist training. The M2 howitzer itself served far longer than anyone in 1941 expected. United States Army artillery battalions used it as their primary light howitzer through the Korean War, where its rapid-fire capability proved decisive in defensive battles. The gun saw extensive service in Vietnam, keeping fire-base perimeters from being overrun through sustained fire support. The M2 remained in Army service until the 1990s. Total production exceeded 10,000 weapons. For a design that began as a modest improvement on World War I-era howitzers, that represents a remarkable service record. But the M2's real legacy isn't the weapon itself. It's the doctrine it enabled and the standard it set for what artillery should prioritize in modern warfare. Modern self-propelled artillery has moved beyond towed howitzers to automated systems with digital fire control and GPS guidance. The M109 Paladin can fire 4 rounds per minute, then displace before counter-battery arrives. The German PESH 2000 can fire 10 rounds in 60 seconds using burst fire modes. These capabilities trace directly back to the World War II revelation that rate of fire matters more than incremental improvements in accuracy or range. That German test officer at Hillersleben in 1943, watching a captured American howitzer outpace everything German artillery could field, he was witnessing the future. Artillery warfare had shifted from careful precision to overwhelming volume, from professional gunner expertise to mechanical reliability, from theoretical performance to practical effectiveness. The mathematics were simple and brutally clear when examined objectively. A howitzer that reliably reached the battlefield and sustained rapid fire was infinitely more valuable than a gun with superior specifications that broke down before engaging the enemy, or required constant maintenance that front-line conditions couldn't provide. An artillery battalion with 80% operational guns could execute missions that a battalion with 40% availability simply couldn't attempt. German artillery consistently failed this fundamental test throughout the war's second half. American artillery consistently passed it. Hillersleben testing had proven this beyond any reasonable doubt by mid-1943, even as German commanders continued deploying howitzers that looked professionally engineered but couldn't be relied upon when needed most. The captured M2, that single howitzer tested exhaustively at German proving grounds for months, told the entire story through its mechanical reliability and consistent performance. Every test firing without failure was evidence that American artillery development had taken the correct path by prioritizing practical function over theoretical optimization. Every comparison between M2 and German howitzer performance proved that industrial maturity and sound engineering principles based on commercial manufacturing experience mattered more than military tradition or precision craftsmanship, pursued without regard to field conditions. The testing data was comprehensive. The conclusions were unavoidable. The implications were devastating to German confidence. America had built artillery, optimized for industrial-age warfare, and German industry couldn't match it, not through better training, not through superior doctrine, not through engineering excellence. The gap was fundamental, rooted in decades of different industrial development and incompatible design philosophies. That single M2 howitzer, unremarkable in appearance, represented industrial and doctrinal sophistication Germany had never achieved. What it demonstrated through months of systematic testing was more threatening than superior specifications or impressive range figures. It proved that America had solved problems German artillery doctrine hadn't recognized, needed solving problems of sustainability, maintainability, operational flexibility, and crew training efficiency. The gun itself was eventually lost, destroyed, captured, or scrapped in the war's final chaos. The testing documentation survived, scattered through archives, preserved by engineers who understood its significance. Those reports, written in precise technical language by German artillery experts, stand as testament to professional military analysis, confronting uncomfortable truths about comparative capability. The M2 howitzer didn't win World War II through technical superiority in any single category. It won through industrial superiority, expressed as mechanical reliability, consistent availability, and ease of operation. German engineers at Hillersleben understood this by mid-1943, documented it thoroughly, and reached correct conclusions about American advantages. But understanding a problem and solving it are fundamentally different challenges. German industry lacked capacity to retool artillery production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its manufacturing practices over decades of commercial competition and simply extended those mature principles to military production with devastating effectiveness. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.